Energetics of solution formation, section 3 of this chapter. I should probably talk about that one, though. So we can think about solution formation happening as 3 different steps. First, we have to separate the solute into individual particles. Okay, the solute particles are attracted to each other by intermolecular forces, and to get them to separate requires some energy. So this step is always going to be endothermic. You have to put energy in to push the solvent molecules apart from each other. So the enthalpy change for that is going to be positive. And then we have separating the solvent particles. So imagine, you're putting a chunk of sodium chloride in a beaker of water. Well, you have to separate the sodium and the chloride ions from each other so it can dissolve. That's what we're talking about. That's also going to require energy because they're attracted to each other. So the enthalpy change, the first one was, I talked about the solvent, and the second one was the solute. Sorry, that's why you're all staring at me? Maybe. Anyway, we have to separate the solute into particles and separate the solvent into particles, and that requires energy. Then, when you mix the solute and the solvent particles together, that's going to be exothermic because the energy is released as the particles interact. In order for the solution to form, there has to be some attraction between the solvent and solute particles, right? The intermolecular forces have to be similar. And so when they are allowed to interact, that's going to be exothermic. So the enthalpy change when you allow them to mix is going to be less than 0. So if we look at enthalpy of the solution forming, the energy change when the solution forms, it's the sum of the changes for each step. And whether that overall sign is positive or negative depends on the magnitude of the individual changes. So solution formation can be exothermic or endothermic. When you mix 2 things together and the solution gets cold, it's absorbing energy from the surroundings. That's an endothermic change. Some things you mix together and they get hot, and that is an exothermic change. So here's an example of an exothermic change when a solution forms. We have the solvent and the solute, and they're attached to each other by intermolecular forces or by ionic bonds, and then we separate the solute into individual particles. We have to put energy in. And then when we separate the solvent into individual particles, that requires putting energy in. When we allow them to mix together, that releases energy. In this situation, more energy is released than had to be put in. And so this solution would probably feel warm to the touch. Yes?
I know through laws of diffusion it's supposed to spread out evenly, but does it actually spread out evenly, or is it like at one point this part's more concentrated, at one point this part's more concentrated?
It will spread out evenly. How long that takes depends on some other factors. If you wait an infinite amount of time, it will mix thoroughly. If you just stick a solid clump of sodium chloride in a beaker of water, it's not instantly going to dissolve and form a homogeneous solution. You may have to wait a while. If you stir it, that will happen a lot faster. Heating makes it happen faster too, because the solvent particles in here are moving, and how fast they're moving depends on the amount of kinetic energy, depends on the temperature. So a hot solution, the particles are moving faster, and so they are essentially stirring themselves more rapidly than if it's cold. This is an example of an endothermic process. We have to put energy in to separate the solute particles and to separate the solvent particles, but here the amount of heat that's released when they mix is less than what we had to put in. So energy has to come in from somewhere, and typically we observe that happen as this solution becomes cold. So we can look at these in different terms. What we do is we take the enthalpy change for the solvent and the enthalpy change for mixing, and we call that the heat of hydration. and that's for aqueous solutions. So when we're mixing an ionic compound in water, we'll combine the solvent energy change and the mixing energy change into the heat of hydration. That's always going to be largely negative, exothermic. And then the heat of the solute being separated, that is the same as the lattice energy, but opposite in sign. Remember, lattice energy was the amount of energy released when you allow ions in the gas phase to come together and form that lattice. Well, this heat for the solute of separating it into individual particles is the opposite process. And so it's the same amount of energy, but opposite in sign. So the heat of solution is the energy required to separate the solute, plus these two terms, which we call heat of hydration. And this solute term is going to be the opposite of the lattice energy. So what we observe is that if the amount of energy needed to separate the solute particles is less than the heat of hydration, the solution process is exothermic, the solution gets warm. If this is larger, then it's endothermic and the solution gets cold. And compounds like this, this is the basis for some instant hot and instant cold packs. You know, you break a little seal inside and you squish the bag around and the bag gets cold. It's like magic, right? That's an endothermic enthalpy change when it becomes a solution. And so it becomes cold and you can use it as an ice pack even though you didn't have a refrigerator or a freezer. And other things will become hot. Sometimes you need a hot pack. You have a sore muscle and you want to put some heat on it. Mix the two things, the solution gets hot. Never mind. So, any questions about that?